Now have a look at this theorem. If f of x is differentiable in convex set C, then the function f of x being convex occurs if and only if we have this following identity, that f of x plus y minus x transpose grad f of x is less than or equal to f of y for all points x and y in C. Now, this looks a bit mysterious, but it's got a very straightforward geometric interpretation, this condition. What it says is that the tangent plane, which is this left-hand side, tangent plane, when you consider this left-hand side as a function of y, this is the tangent plane at the point x, is always less than the surface, less than or equal to, technically, as a function of y. Right, so the surface always sits above every tangent. Now, it's an if and only if, so there's two sides to this proof, and we'll do the forwards implication first. That is, we are given that f of x is convex and aim to prove this identity. And we'll use the identity that we just established for convex functions g of t. That g of 1 is bigger than or equal to g of 0 plus g dash of 0. Okay, so how do we use that? Alright, so f is convex, so for every points x and y in C, let's define g of t to be the function f of x plus t into y minus x. Because the convexity of f, g of t is convex. Because g of t is convex, we know this identity holds, so we're going to use that. Now here, we've got g as this particular function f. So here, we know some of these things. We know g of 0 is f with that term missing, so that's f of x. We know g of 1, put t is equal to 1 in here, the x's cancel, this is f of y. And now what's g dashed of 0? Well, let's have a look at g dashed of t. From this formula, we can derive the derivative via the chain rule. And it's the sort of thing we've done before, and we know what the answer is. It's y minus x transposed grad f of x plus t y minus x. And hence, just put t is equal to 0. G dashed of 0 is this evaluated with t is equal to 0, namely y minus x transpose grad f of x. Okay, put it into this identity, and what have we got? We've got g of 1, well g of 1 is f of y, is bigger than or equal to g of 0, g of 0 is f of x, plus g dashed of 0, and g dashed of 0 is just this, so that's plus y minus x transposed grad f of x. And that holds for all x and y in the convex set C, so we've established this property here. Right, now we're going to prove the reverse implication. Given this identity for all x, y and C, that the function f of x is necessarily convex. Right, so the starting point is, this is the identity there, for all, holds for all x, y in the convex set. Now what the idea is the following. For any given x and y, what we do is look at the function along the line segment joining those 2 points. So notionally there's x, there's y, and the function f, say, looks like that. Now have a look at what happens for every z on the line segment joining x and y. So say z is there, there's f of z. Let's draw in the tangent, and what we appreciate is that the function surface is above this tangent plane both at y and at x. Right, so let's see the implications of this via the algebra. Right, so write down this identity twice for the tangent plane based at z. So that means f of z plus z minus plus x minus z transposed grad f of z has to be less than or equal to f of x. That's looking here. Now looking over here to y, we've got a similar statement that f of z plus y minus z transposed grad f of z has to be less than or equal to f of y. Right, now let's simplify this a little bit by replacing the z's in here. Right, now z is some point in between x and y, so let t measure how far we are between x and y. So we know that z will be tx plus 1 minus ty for some t between 0 and 1. And hence x minus z is x minus tx plus 1 minus ty. You can see there's a 1 minus tx here and a 1 minus t there, so there's a common factor here. This is 1 minus t into x minus y. And let's have a look at y minus z. So y minus z is y minus, there should be a minus there, otherwise I don't get the minus there. Okay, y minus tx minus 1 minus ty is equal to what? Well, this plus y cancelled out with a minus 1y there, leaving us with a plus ty. So let's write it as ty, and then there's just the minus tx. So factoring out the t, that's just minus x. So these two identities become together f of z plus 1 minus t x minus y transposed grad f of z is less than or equal to f of x, and f of z plus t into y minus x transposed grad f of z is less than or equal to f of y. The question, and we won't replace the z's there. Now, what do we do with those two? We combine them to try to cancel out this stuff. And the combination is to take t times the first and add it to 1 minus t times the second. And then what do we get? Well, we get t f of z plus t into 1 minus t x minus y transposed grad f of z. Then also on the left hand side we have plus 1 minus t f of z plus t times 1 minus t times y minus x transposed grad f of z. Then we've got less than or equal to. Now both of these are positive things, so the inequalities stay there. So this sum is less than or equal to t f of x plus 1 minus t f of y. Now you see the beautiful thing is that we cancel these two terms, these big messy terms, because they're exactly the same, except one is x minus y and the other one is y minus x. So there you go. And what happens to the f of z term? Well, it's t f of z plus 1 minus t f of z, so the t parts cancel, and we're just left with an f of z on the left. But remember, z is this, so that's f of tx plus 1 minus ty. And on the right hand side is t f of x plus 1 minus t f of y. Right, and we've derived that this inequality must hold for every pair of x and y in the convex set for all t between 0 and 1. And by the definition of convexity, that implies that f is a convex on that convex set C.